Hello. Oh, I didn't erase the board. Oh, I almost did. We're still talking about number systems. We just left home base, so to speak. I did that accidentally. The comfortable, old, worn-out shoe of base 10, the numbers we've been counting with ever since we can remember. But this is going to be a different number system. It's not base 8, but this is video 8. And I need to label it. There, 8. What other number systems could there possibly be? Oh, I don't know. The one that we really, really need if we're going to talk about computers, the binary number system, B-I-N-A-R-Y. And I think I put in parentheses what the other alternative name of the number system is. This one is base 2. Thus binary. Cool how that works out. And whereas in base 10 we had 10 digits to work with, in base 2 we got 2 digits to work with. 2 digits. Let's see. I think the 2 digits are 6 and 9. Feel free to yell at your YouTube screen. No, of course they are zeros and ones. 0, 1. That's it. Any number we want to represent in binary has to be nothing but zeros and ones. How many times have I said that? I'm driving myself crazy with all that. Here is a place value chart for the binary number system. I'll fill in the columns as I go across with both the actual place value and why it's that place value. This is 2 to the 0. Looks like 2 degrees. 2 to the 0 power, anything to the 0 power. If you recall way back from the last video, anything in 0 power is 1. I lied. I said I was going to fill in all the column information as I go across. I'm not. I'm going to fill in all the powers first. That's 2 to the 0. Here's 2 to the first, 2 to the 2th, also known as 2 squared, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, yada, 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 dot, dot, dot. Now I'll do the numbers. Oh, no, I can't do exponents in my head. Well, just like as we went to the left, I didn't even leave you time to lament and think about that. But just as we go to the left in base 10, we multiply by 10 each time for each column. In binary, every time we take a notch step to the left, we double it. We multiply by 2. And we can multiply by 2 real fast without having to do any exponents. 2 to the 6th power. Oh, no, that's all that multiplication. No. Watch this. 1, double it. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. Being a computer person does crazy things to your brain. You get all these numbers and stuff like that stuck in your head and you can't get rid of them. Now then, now I got to fill in the number under here. Now I'm in binary 5th grade school. I don't think we did this, not 5th grade. I don't think we did this in 2nd grade, but it's exactly the same principles as what I did with the place value chart for base 10. I'm going to fill in a number starting with this column. A 1 under 32's place. 1, 1, 0, 0, 1, 0. Now, that's going to get a little subscript of 2. Why, do you ask? Well, it turns out, since those are all valid digits in base 10, unless I specify explicitly by putting a subscript and saying, this is a number representation in the binary or base 2 number system, for all we know, it could be base 10. It could be 110,010. That's a legitimate base 10 number. But in this case, that's not the value of that. No, no. We still got to play that same game we did before. We've got to multiply each digit times its place value in the place value chart. So that 1 does not mean 1. It means 1 times 32 plus 1 times 16 plus, see how this works? This is exactly the same thing we did with base 10, except now it's probably, I hope, insulting your intelligence ever so slightly less. We'll see. 0. 0 times 8 plus, I hope I don't leave a notch out, 32, 16, 8, 32, 16, 8. 0 times 4 plus 1 times 2 plus, I almost made it to the end over there, plus 0 times 1. Now, the cool thing about trying to find out what the hey that number is back in base 10, that's where we're headed here. What we're doing is converting from base 2 to base 10 to find out what the number, air quotes here, really is. It really is this in the computer, but we want to find out what it is back in our good old comfortable base 10. We got to do the math, the easy math, because everything is either multiplied by 1 or it's multiplied by 0. I can do that math in my head. 1 times 32 is 32. 1 times 16 is 16. 0 times 8 is 0. 0 times 4 is 0. 1 times 2 is 2, and 0 times 1 is 0. So this is easy math. I could put that in a column and probably add it up more easily. Let me see. 16, 17, 18, 19, 20. I think it's 50. 50. And now I'll explicitly put the little subscript of 10 because we've left binary behind after we do all this math. What we did was figure out what the number really is in base 10. That's what 50 looks like in the mind of the computer. It's a bunch of zeros and ones like that. Now, you might well be asking, here's a little extra for experts. Why do we have to limit ourselves to just zeros and ones? Because this is like a nice little simple number system. Why don't we allow 2 as well? Here's a problem with that. Just scratch work area. 2, 0, base 2. What would that be? Well, let's see. 2, 0, base 2 would be 2 times 2. That would be 4 in base 10. How simple. There's a problem with that, though. What about a 1, 0, 0 in base 2? Throw that on your handy-dandy place value chart, multiply, add it up, and you're going to get 1 times 4, 0 times everything else. That's 4 in base 10. Well, what about what looks like a 12 in base 2, since we're allowing digit 2 now? That's a 1 times 2 plus a 2 times 1. Whoops. And there, ladies and gentlemen, therein lies the problem. If we have more digits available than we have in the name of the base, then we have ambiguous representations. There's not a one-to-one correspondence. There's not a unique way to represent 4 in the computer if we allow too many digits. Here's 3 different ways to represent just 4, and that's a pretty small, simple number. It gets bad in a hurry when we start looking at big numbers. So let's not go there. Erase the blue stuff from your mind, just as I erase it from the board. Stick to the zeros and ones. I'm going to slip the aside down here this time. Remember that insulting aside that was up in that corner? Well, anybody knows that. Maybe not. Let me see here. Question. What's the largest number? Whoops. Excuse me. What's the largest binary number in 8 bits? We could ask this question for any number of bits. If we use too few bits, it's become so trivial that we could figure it out in our heads. Maybe this one we can, maybe we can't. What's the largest binary number in 8 bits? Mapping back to the corner aside up there. Well, answer. It's the smallest, S-M-A-L-L-E-S-T, non-trivial, I'll abbreviate, non-triv. That's the intelligent abbreviation for that. Oh, it's the non-triv number. It's the smallest non-triv number in 9 bits minus 1. Ta-da! That was easy. Well, maybe. Let's see here. We have here's the figure. That goes with that question and answer. Here's the picture. 1, 2, 3, 4, 5, 6, 7, 8 bits. 8 bits to fill in. 8 zeros and ones, and I want to max that out. The largest number I could possibly represent. Well, the largest digit I have is 1s. So I don't get to fill this with 9s all the way across the way I did in the assigned base 10. This is going to be 1s. 1, 1, 1, 1, 1, 1, 1, 1, base 2. Done and done. And if we're working in binary, we're going to stay in binary. There's no problem with that. Here's the problem with that. If we want to know what this really is, and I'm going to stop doing those air quotes, we got to slap this on this place value chart up here and look at all the math we got to do. It's going to take up 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. Let me read these numbers off while you add them in your head because I don't have room to write them on the board. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. You got it? The answer is, I don't know. Let's look and see. You know what? Let's fill in 9 blanks. I didn't leave much room for 9 blanks. 1, 2, 3, 4, 5, 6, 7, 8, 9. There they are. The smallest non-trivial number in 9 bits I can represent has to start with a 1. If I put a 0 there, I'm not technically taking up 9 bits. That's why it has to be non-trivial. The rest of them can be zeros. It's still in base 2. It's still a huge wide number. Takes up lots of space on this place value chart. Oh, and the -1. But watch this. 1, 2, 3, 4, 5, 6, 7, 8, and then the 9th. 1, 2, 3, 4, 5, 6, 7, 8, 9. Visualize this, if you will. A 1 right here, and zeros everywhere else. I can do that math. A 1 right here, and then zeros everywhere else when I expand it out and try to add it up. That's 1 times 256, also known as 256, base 10. The 1 with solid zeros taking up 9 bits is 256. -1, I can even do that math. That's 255. What's the moral of the story? You don't have to add all these up. You don't have to add 128, 64, and so forth and all that. Whatever that number is, with all those solid 1s, it's 1 less than this number. This number is easy to get. There's only one place value multiplication to do. 256 minus 1 is 255. We're so impressed with that, how easily we got that we'll circle that. Now, that was an overlay on top of decimal, and that's why I dragged you through all that stuff in video 7, just to establish a pattern so that we could see how we're going to be looking at number systems. And I guess we're done, huh? Binary, that's all the number system we need. Oh, wait. If you thought the clouds got thick when we moved from decimal to binary, you, ladies and gentlemen, are about to experience a hurricane, or at least a thunderstorm. We have one more ominous number system to go, and you can't wait to see that in video 9. Video 9. Video 9. See you online.